Hello everyone, welcome to the class. I hope you're all doing good and you are in the best of your health. So we're learning the concept of rotational motion. We have learned so many things. Concept related to moment of inertia, concept related to kinetic energy associated with combined rotation and translation motion, concepts of angular momentum in combined rotation and translation motion. Today we'll be studying about rolling motion. Now before starting the concept of rolling motion, let me tell you, can you imagine a tire? You must have ridden a bicycle and you must have seen the tire is performing a rolling motion. It's rotating also and simultaneously it's in a translation motion also. So in such kind of motion, let's study what variables we need to use. See here, so let's study about rolling motion. In rolling motion, we'll be provided an object which can simultaneously rotate and move in a translation motion. Now I told you all to imagine a tire, a cycle wheel you may imagine, which is rolling on a horizontal ground. Let's say this is the wheel of a bicycle. Now as it rolls, observe this point A which I have marked here. As it rolls, it will simultaneously go up at the topmost point and again it will come at the bottommost point. Let me show you its various position as it performs the rolling motion. So as it performs, it will be moving on this horizontal ground. This is the second position. Let's say A, after it was initially here, it has reached to some point, let's say here. So I'll mark this point A here. Now after reaching here, it would reach to the topmost point. Let's say it has reached here after moving some more, after performing some more rotation, it would have moved in this way and it would have reached a topmost point. Further, let's go ahead and let's perform one complete rotation. How will the position of A change? So let me show you as it moves further, it reaches here. Let me show its position has reached here. And now again at the last, when it reaches again at the bottommost point, it will reach. I know that you cannot see all the 5 positions of A simultaneously, it will be very difficult, but okay for us. I will show you simultaneously one by one each of the position of the point A. And let's say finally it reaches at the bottommost point, that is A. So I've shown you all the 5 positions. You see here, A was at the bottommost point here, then A reached here, then A reached at the topmost point, you may see here, then again further A reached here and A reached here. Now suppose this wheel has a radius r. If I mark the radius of the wheel as r, then in one complete rotation, it would have traversed linearly a distance of 2 pi r. That's quite simple for us to know that. So it has moved a distance of 2 pi r in one complete rotation. That's quite obvious for us to understand because we know that perimeter or circumference of a circle is 2 pi r. It's very easy for us. So linearly, after one complete rotation, the wheel would have moved a distance of 2 pi r. Let us show this is the center of the wheel. This is the center of the wheel. Let's call it as O. It is moving in a translation motion. You can see that it is moving linearly. What about point A? Point A is not moving in a linear fashion, rather it's moving on an arc-like path. Let me show you. If I connect all the positions of A, this is the path which A would have traversed as it moves along the wheel. Now see, as wheel rotates, this path of A would be somewhat like this. You can see here, it would be somewhat like this. This is actually a cycloid-like path. And now see, when the wheel rotates through a linear distance of 2 pi r, when it makes one complete rotation, let's find out what is the linear distance traversed by A. That means what is the length of this dotted path which I have shown you here. Let's find out what is its path. Do you remember? We also derived the velocity of any particle of any point on a disk or on a wheel. That came out to be 2v sine theta by 2. I hope that you would have seen the class and you will be easily recalling that. If we talk about, if I connect these 2 points, if I say this angle is theta, then if you remember, I told you the velocity of this point will be nothing but 2v sine theta by 2. Hope you can easily remember that. Now, in a very short interval of time, this point A would have traversed a linear distance of ds is equal to velocity into small time. Its velocity is 2v sine theta by 2 multiplied by the small time, that is dt. This is the small linear distance traversed by this particle in a very small time called dt. Now dt, what we can write dt? Dt can be written as d theta by omega. That's quite simple. So let me write dt as velocity 2v sine theta by 2 and dt as d theta by omega, where omega is the angular velocity with which the wheel is rotating. Here one thing we are taking that the wheel is moving with a constant angular velocity, and since if the angular velocity is constant, the linear velocity will also be constant of the center of mass of the wheel. Linear velocity will be constant, that will be equal to v equals to r into omega. That's quite simple to make out. So I'm writing one more point. Here linear velocity of the center of mass will be related with omega as v equals to r into omega. If we open v as r into omega, see what things we can mention out. We can write ds is equal to, let's open v as r into omega, 2 r omega sine theta by 2, and we can write d theta by omega, here d theta by omega. We can easily see that omega and omega can be cancelled out. That's quite obvious. Omega and omega can be cancelled out. Let's cancel out them. We'll be left with 2r sine theta by 2 into d theta. Now, in one complete rotation, when it goes on rotating, can you imagine what will be the angle that this particle would have moved overall in one complete rotation? That is quite obvious. That is 2 pi. In one complete rotation, this angle would have moved from 0 to 2 pi. When theta is equal to 0, the point was at this position. When theta is equal to 2 pi, the point is at the bottommost position again. So if we integrate this entire equation, we can get the linear distance traversed by A in one complete rotation. So now I'm going to find out net linear distance traversed by A as S. That will be equal to integration of ds. That will be equal to integration of this equation. 2r we can take constant, and sine theta by 2 d theta. We have to integrate this part. Sine theta by 2 d theta is the variable. I hope that you can clearly see till this end. Let me put up the variables. Theta is equal to 0 and theta is equals to 2 pi. This is what we have obtained. Now let's go ahead. Sine theta by 2 integration. We know that sine theta integration is minus cos theta, and whenever here we have a term in division or term, a constant is multiplied with the variable, we have to take it outside and put it in the denominator. So let's see how we are going to make it. Finally, the integration part will come out to be, we have S is equal to integration of 2r. So we have 2r as the constant, and integration of sine theta by 2 will give us, we have to divide this entire equation 1 by 1 by 2, and here sine theta by 2 integration we will get that as minus cos theta by 2. We know that sine theta integration is minus cos theta, so I'm writing here theta by 2 minus cos theta by 2 from 0 to 2 by 2 into 2 4r. That's quite obvious. And here let's put up the upper limit first minus lower limit, and minus sign here, let's take it outside, we'll get minus 4r. So cos 2 pi by 2 minus cos 0 by 2. We'll be left with this. Let's put up the values. Let's see what are the values we'll be going to obtain. Minus 4r, cos 2 pi by 2. 2 will be cancelled out, cos pi. Cos pi is nothing but minus 1. So this will give you minus 1. Minus cos 0 is also 1. We are going to get minus 2. Minus 2 minus into minus plus, we'll get 8r. That is linear distance traversed by the point A in one complete rotation is equal to 8r. So you need to remember a result. Let's come to the diagram once again. You see here A was following this path. As you can see, A is following this path. It's moving along this path. In one complete rotation, the rim would have traveled, the center of mass would have traveled a distance of 2 pi r, and any particle on the rim would have moved a distance of 8r. That means the length of this cycloid path is nothing but 8r. So I'm marking this length as 8r. So let me write down this point separately. Distance traveled by any point on the rim of wheel is equal to 8r. Distance traveled by any point on wheel, by any point on rim of wheel in one complete rotation is equal to 8r. In one complete rotation, so I'm marking one rotation is equal to 8r. That's quite obvious. So we learn two things. First of all, the linear distance traveled by the center of mass will be 2 pi r, and the distance traveled by any particle lying on the rim of the wheel will be equal to 8r. Do remember this result, because in objective questions you can directly answer them. If question is directly put up, what is the distance traveled by any particle or any point lying on the rim of the wheel, that will be equal to 8r. Let's go ahead and also remember this formula. The velocity of any point on the rim is nothing but 2v sine theta by 2, which already we have derived in one of the class. This was the kinematics of rolling motion. Shall we go to the dynamics of rolling motion? And before going to the dynamics of rolling motion, let me explain you all about the concept of rolling friction. You would be very much interested in riding bicycle or riding bike, and you must have seen wheels are rolling. And I told you all, in rolling motion, if you remember, we have derived one thing: the bottommost point is at rest and its velocity is 0, and the topmost point is its velocity is just twice of velocity of center of mass. See what I'm talking about? We are going to understand in which direction and of what magnitude the friction force acts on the wheel. We are going to understand this point. Suppose we have a wheel which can rotate with any angular velocity omega, it can rotate. Now if here you see the surface on which it is rotating and the wheel which is rotating, if both are rigid, we are talking about if both are rigid bodies, that means this wheel is also rigid and this surface is also rigid. When I say rigid, and as the word means, rigid means that cannot be deformed. That means this wheel is touching this surface only at one particular point. Let me call this point as A. At only one point of contact it is touching. And since this particle, its velocity in pure rolling, if you remember, we have derived its velocity and we came out to the result, its velocity will be 0. That means it is at rest. If something is at rest, that means the only friction that can act on it will be static friction. So let me call it as static friction that will be acting on it. Static friction can act because it is not slipping on the surface. In general, but in talk about practical cases, have you ever seen the wheel of the bicycle or your car or your bike? It is slightly deformed at the bottommost position. So let me go ahead with the next figure, which will show the actual scenario. Here in this figure, we will find that the rim of the wheel, which I am showing you in a different way, how it looks like in practical cases. I have shown a bit deformed at this position. That means the normal that the ground will exert, if I mark slightly this surface to be non-uniform, I hope that this slightly jerk that I am giving, hope that you can understand what we are talking about. Let's say it is slightly deformed at this position. Now this wheel is trying to exert a force on this ground. So ground is going to exert a force on it, and that is the normal force. The normal force will be something like this, and the friction force will act on it in this given direction. This will be the sense of friction force. We can see here this friction force is not acting at this point, it will be acting at this point, and this surface is actually not only touching at one point but it's actually touching at a layer of surface. You can see here, because this body will be deformed at the bottommost position. If you talk about a tire, you can think about its bottommost position will be deformed and the normal will be somewhere here acting. Let's talk about where will the normal acting here. The normal of this point, the normal acting on this point will be given in this direction. That means normal is going to pass through the center of mass. So can you imagine one thing? Its torque will be 0 about the center of mass. Its torque will be 0 because it is passing through the center of mass. And let's talk about this. Its torque will not be 0 because it is not passing through the center of mass, and actually this normal is the one force which is responsible to deaccelerate the body because it is producing a torque which is anti-clockwise in sense. And this friction force will be also responsible to deaccelerate the body. But here we find that this force is not responsible to deaccelerate the body. Now, one thing we have learned, when a body is a rigid body and it can rotate, it can move in a rolling motion, remember it is going to touch the surface only at one point, and static friction is going to act at that one point if we neglect the fact it is not slipping or sliding on the surface. But in the case of sliding on the surface, the friction force will actually act, and normal reaction will actually act in the given direction as we have shown here. Now let's study about what is the direction of friction force. I have shown the direction of friction force in this diagram but not in this diagram, to show you all, to explain you all with an example in what direction the frictional force will act in a given scenario. Let's imagine a spherical surface, a spherical body. Let's imagine a spherical body which is under a pure rolling motion. So I'm going to give you an example. Imagine this sphere of mass m and radius r. Sphere, mass m and radius r. Suppose we are going to apply a force tangentially on the topmost point. So here we see, let's say we have applied a force F tangentially on the topmost point, and let's say we have got this radius as radius r of the sphere. Its mass is m, its radius is r. Whenever it's given it's only a sphere, that means you have to take that solid sphere case. So one thing you can make out, its moment of inertia will be 2 by 5 mr square. Now due to the application of this force, let's say it is having a linear acceleration a and it's rotating also, so its angular acceleration is given as alpha. Very easy for us to relate both a equals to r into alpha if it's a case of pure rolling. When I say pure rolling, that means it is not slipping. If it's not slipping, that means a will be equal to r into alpha. Please note that point, that's required, that's important. Now suppose we are required, find out what is the acceleration of this body and what is the frictional force acting on the body. So we are required to find out what is the acceleration of the body and find out what is the frictional force acting on the body. Friction force acting on the body. These are the two things that we are required to find out in this given scenario. Now let's talk about the bottommost point, because this is the point where friction will be acting. Friction can be in any sense. It can be in the forward direction, can be in the backward direction. Now what will be, now let's try to imagine in what direction the friction force will be acting. You see here, this surface, this bottommost surface of the wheel is trying to move in the backward direction. It's trying to slip in the backward direction. So hence friction force will be acting in the forward direction. This easily we can make out. But what I'm going to do, I'm going to show you, you can take the friction in any sense. Either you take in the forward direction, either you take in the backward direction. The equations will give you the result that in what direction friction force is acting. Let's say, again, let's say the friction force acting at this point is in the forward direction, and let me write this as F. I have shown a friction force in a different, a bit elevated, because to show it separately. Let me show it with a different color because two white colors are matching. So you might get confused. Let me show you with a different color. Let's say friction force is acting along the forward direction and its value is small f. this is the direction of frictional force acting on this sphere that we have assumed actually. Now we have to come out with the result, whatever we have taken, whether it's right or wrong. Capital F, this is the external force acting on the wheel at the topmost point tangentially to the sphere, and here we have imagined small f as the frictional force that is acting on the sphere. Its linear acceleration is a, its angular acceleration is alpha, where a will be equal to r alpha. Let's write down the equations of motion. First of all, and we will be using force equations. First of all, seeing the linear motion of the sphere, we can write that since both forces are acting in the forward direction, so F plus small f is equal to mass into acceleration, equation number 1. Very simple to obtain. Now what about the rotational motion? It's also rotating. That means we can frame one more equation. It's rotating about this center, its center of mass. And this center of mass would be moving linearly. So seeing the rotational motion, linear motion we have seen, now let's talk about its rotational motion. I hope that you can clearly make out whatever I am writing here. Rotational motion equation, capital F force which is acting, its torque. See its torque, R cross F is the torque. If I take R in this direction, so my finger is in this direction, I have to curl my fingers, my thumb is pointing into the plane of board, and this torque, its rotatory sense is in the clockwise sense. So let me take it as positive. So F into R will be the first equation. Other force which is acting at the bottommost point, that is the frictional force. Now if I take its torque, R vector will be directed in the downward direction. Let me show you. This is also R. Now you see here, R cross, if I take, my fingers are curling in the anti-clockwise sense. That is, it is trying to resist this rotatory motion, and thumb is pointing out of the plane of board. That means it is acting opposite to the torque which was given by this force. So let us take, because we have taken positive sign in the direction that is into the plane of board, so we have to take negative sign for the direction out of the plane of the board. So let me write this as torque as minus Fr is equal to I into alpha. So let me write this as I into alpha. Let me open up this equation. We'll be having F minus F into R is equal to I, moment of inertia of a sphere for this axis will be 2 by 5 mr square, which we have taken, and alpha we can replace as A by R, because I have written A equals to R alpha, so alpha can be replaced as A by R. 1R will be cancelled out. Here also 1R is there, it will be cancelling out the total R square. So we will be having this entire R will be cancelled out. F minus F will be equal to 2 by 5 ma. This is what we will be left with. F minus small f is equal to 2 by 5 ma, equation number 2. Adding both 1 and 2, we can see that small f will be cancelled out. So f plus f, 2f will be equal to ma plus 2 by 5 ma, that will give us 7 by 5 ma. So adding equation number 1 and 2, we will be left with 2f is equal to 7 by 5 ma. 1 plus 2, this will give us 2f is equal to 7 by 5 ma. Very easily you can add. So finally we are going to get acceleration as 5 into 10, 10f by 7m. So first thing we obtained the acceleration, the linear acceleration we obtained, that is equal to 10f by 10f by 7m. Next thing, we also require what is the frictional force acting at the bottommost point. Using these two equations, easily we can make out equation number 1 and 2 you can use, and you can find out the value of small f. Now if from equation number 1, if we subtract equation number 2, we can see that small f will be cancelled out. So let me use this. From equation number 1, I am subtracting equation number 2. So we will be left with f plus f, and this will, capital F capital will be cancelled out. Small f minus minus plus, so it will be having 2 into small f is equal to ma minus 2 by 5 ma, so we will be left with 3 by 5 ma. Substitute the value of acceleration from here. So we will be getting 3 by 5 capital M multiplied by acceleration A, that is 10f by 7m. 10F by 7M. M and M cancelled out, and here we are left with 2F. Now see here, 2 and this will be cancelling out 10, it will give us 5, see here, and 5 and 5 can be cancelled out, we will be left with 3, and F is equal to 3, MM will be cancelled out, 3F by 7. M and M will be cancelled out, so small f comes out to be 3 capital F by 7. 3F by 7, this is what we have obtained. This is the value of friction force that has to act at the bottommost point so that this body can perform pure rolling motion. Now one more thing, since we have taken this as static friction has got a limit, and its limit is mu into n. So here it's if the coefficient of friction is also provided mu. So this friction force that is given, that should be less than or equal to mu into n, because we know static friction has got a limit. To understand this limiting friction case, let us talk about a case when we are going to take a cylinder which can actually roll and come down on an inclined plane. Let's go to the next case. And before going to the next case, let me give a quick recap what we have done in this case. Once again, very quick. This was a sphere, a solid sphere, which mass and radius were given to us. A tangential force was acting. Now, whenever a force is given to us, so its torque is actually helping this sphere to rotate. I told you all, we don't know anything about the friction force, in what direction it is acting, in the forward direction or in the backward direction. So, what we will do, we will generally apply force in any direction, the friction force. Here we have applied it in forward direction. Later on, the equation will give us whether the direction that we have taken is right or wrong. Now, in our result, we got that friction force comes out to be somewhere around, it was 3F by 7. That means it came to be positive. That means whatever direction we have taken, that direction is correct. So hence, friction force is going to act in this direction, that is right hand side, that is forward direction. This is what we have obtained. And remember, you can frame two equations, one due to the linear motion and one due to the rotational motion. And again, I am repeating, you can take friction force in any direction. In next example, I will show you when I am going to take friction force in the backward direction. Let's go to the next example. And hope you are simultaneously able to get to realize in what direction we have to take the direction of frictional force. Have you realized one thing? Have you imagined one thing in this case? Always, now see, when an object is a rigid body, I'm talking only about linear motion. If you take a block and let it move on a rough surface, we know that the friction force acting on it is generally in the backward direction, which is opposite to the relative motion of the surface, the two surfaces in contact. Here, have you observed one thing? The friction force was acting in the forward direction. And if you are thinking, why is it in the forward direction? Because imagine the bottommost point that I have shown you. Imagine the bottommost point. This bottommost point is actually trying to move in the backward direction. This bottommost point, which is touching the surface, it's actually trying to move in the backward direction. If it is trying to move in the backward direction, that means its relative motion with respect to surface is towards the left hand side direction, towards the backward direction. Hence, friction force has to act in the forward direction. That is the logic behind it. So we are not disturbing any law, okay? So hence, friction force is acting in the forward direction. Let's go ahead with a different scenario. The scenario is this. In this case, we have a cylinder. Second example, we have a solid cylinder. When I talk about only cylinder, when I say only sphere, you have to think on your own. We are talking about solid objects. That means either it is a solid cylinder, and if I say only sphere, it's a solid sphere. In your questions also, when it's given that a sphere is rolling or a cylinder is rolling, you have to take that object as solid object. Do remember this. A cylinder, again, mass m and radius capital R. Let's say we have taken its mass as m and radius as capital R. Rolls on an inclined plane. Rolls on an inclined plane. Now here let's say angle of inclination is given as theta, which I will show you in the figure also. And let's study the variables, what will be their magnitude and what motion it will be performing, and what is the acceleration and what is the value of friction force that is acting. Here the body will be somewhat like this. Let's say this is the inclined plane on which it is rolling. We will be finding out with the given variables what is the linear acceleration of the cylinder. Let's say this angle is given as theta. This is the angle, this is given as theta, and let's say the cylinder is rolling. This is the cylinder of mass m and radius r which is rolling. It is touching only at one point of contact. Whenever we talk in any case, we are not going to take the practical case, we are only going to take the two surfaces are rigid surface and there is no deformation at the bottommost point. And in separate cases, whenever deformation is given separately, then we have to take what will be the direction of normal that will be acting and what will be the value of friction force that will be acting, that we will see later on. Here you see this surface is touching only at only one point. The normal force that will be acting on this cylinder will be in this direction. Again mg will be acting along shown direction. Although I should show mg to be coming from here, but I have shown here so that for the clarity of the figure. Next, see here, mg's two component, mg sin theta and mg cos theta will be acting. Let me show you here mg two component. Mg sin theta I am marking from the center of mass. Mg sin theta will be acting here and mg cos theta should be acting here. So let me show you here mg cos theta separately. This force which I have shown, that is actually equal to mg cos theta. Friction force, I have to also show you the friction force acting on this cylinder. Let us take the friction force is acting this time in the backward direction. So let me show you separately, the friction force is acting in the backward direction. To understand the forces which are acting, we can also draw the free body diagram. But already we have shown so many free body diagrams, you can make out. For the linear motion, we have to consider mg sin theta and friction force. Let's say the coefficient of friction which is acting between the two surfaces is given as mu. Mu is the coefficient of friction. Okay, I will write it separately so that you may make out. Mu is the coefficient of friction which is existing between the two surfaces. Now let's try to find out what should be the value of mu for pure rolling to perform. Now it is rolling, it's a pure rolling case, it's not slipping. Let's say its linear acceleration is a. It is also rolling, it will be having an angular acceleration, let's call that as alpha. So alpha is the angular acceleration, a is the linear acceleration. How they will be related? A will be equal to r into alpha. First thing, this we know, a equals to r into alpha. Let's frame equation, two kinds of motion it is performing, linear motion and rotational motion also. So for linear motion equation, if we frame the linear motion equation, we will be having capital, now see here the external force that is acting, that is the force due to gravity, that is mg sin theta. There is no other force, no external force acting, only mg sin theta will be acting. Mg sin theta in the right hand side, friction force in the left hand side. So mg sin theta minus small f will give us mass into acceleration, equation number 1. Second equation will be due to the rotational motion. Now you see here, the rotational motion will be only due to the frictional force. Friction force is acting here. Friction force is acting here. So the torque that will be developed due to the friction force, that will be equal to F into R. So let me mark here in the rotational motion case, checking its rotational motion. Rotational motion, the torque acting due to the frictional force. Now you see here, torque of frictional force, R vector will be downward, R cross F, it is going to rotate the sphere, the cylinder in the clockwise sense, r cross f, and the thumb is going into the plane of board. Its sense will be clockwise, it's rotating in this way, and my thumb is pointing into the plane of the board, thumb is pointing towards the direction of torque, fingers are curling along the sense of rotation. Let's take the direction into the plane of the board as positive, so its torque will be F into R. That will come out to be I into alpha. First thing. Now I will be half mr square. Let's put up that. F into R is equal to half capital M R square. Alpha value is nothing but A by R. So let me put here A by R. Here you see R will be cancelled out. We will be left with small f is equal to half ma. Small f is equal to half capital Ma. This is what we have obtained. Small f is equal to half into capital Ma. This is what we have obtained. Let's mark this as equation number 2. Equation number 1 is here. Equation number 2 is here. We can add equation number 1 and 2 so that small f will be cancelled out and you can find out the value of A. So adding equation number 1 and 2, 1 plus 2, we will be getting mg sin theta minus f plus f will be cancelled out is equal to ma plus half ma, that will be giving us 3 by 2 ma. will be cancelled out, A will come out to be 2 by 3 g sin theta. Obtain the value of acceleration. Easily you can obtain the value of frictional force from here. But substitute the value of acceleration, you can obtain the value of friction. So frictional force will come out to be F is equal to half ma, half m, A value 2 by 3 g sin theta g sin theta. This is what we have written here. So we will be getting 2 and 2 will be cancelled out, mg sin theta by 3. So let me write finally it will be 1 by 3 mg sin theta. This is the value of frictional force acting on the cylinder shown. This is the value of friction force acting on the cylinder shown. You see here we are getting friction force as positive. That means the direction we have taken, that is right. That means friction force is acting in the backward direction. I want to see you the diagram. That means the friction force will be acting in the backward direction, and actually this force is responsible for the cylinder to rotate. Now one more thing, friction force is developed due to the roughness of the surface, and it has got a limiting value, that is mu into n. N will be equal to mg cos theta. So we know friction force has to be less than mu into n. So let me write one more equation. We got the value of friction force, we got the value of acceleration, and we know one thing. Friction force should be less than or equal to mu into n. Substitute the value of n as mg cos theta. So we'll be getting F is less than or equal to mu mg cos theta. This is the value that we can put. Friction value is 1 by 3 mg sin theta. So 1 by 3 mg sin theta is less than or equal to mu mg cos theta. From here you see mu mg will be cancelled out. Here we can take cos theta here, so mu should be greater than or equal to 1 by 3 tan theta. So mu has to be greater than this value. So I am writing this separately again. Mu should be greater than 1 by 3 tan theta. This is the minimum value of mu. For pure rolling, the minimum value of coefficient of friction should be 1 by 3 tan theta. So I am writing this result separately. For pure rolling, mu should be greater than or equal to 1 by 3 tan theta. This should be at least the value of coefficient of friction. It has got no maximum value. You can increase the value of coefficient of friction. Still the body will in a pure rolling motion. And if the value of mu is less than this, the body will start sliding. That means it's going to slide over the surface, it's going to slip over the surface, and it will perform a pure linear motion. So I believe that you would have understood when I say mu should be greater than or equal to 1 by 3 tan theta. Hope you can analyze more thing about this motion, and we'll see more examples in the next lecture. Till the time, do revise this, do practice more questions. You'll be finding that it's easy, simple and interesting. So I believe you'll be practicing more questions. I'll meet you all in the next class. Till the time, thank you everyone. Meet you all in the next class. Wish you all the very best. Thank you.